Another interesting type of interference pattern we see with sound are what we call sound beats. Now, sound waves do interfere in the same way that other waves do in space. And so whenever you have areas where um, the crests of a sound wave meet each other, you're going to end up with a louder tone. And in areas where you have a crest meeting up with a trough, you're going to have destructive interference. You're going to have an elimination of sound. So here at point C, someone is going to hear a much louder sound than either speakers A or B because it's a combined amplitude. So it's going to be very loud for somebody at point C. But somebody at point D will not hear anything because he's in a point where he would hear destructive interference. But what if these two frequencies are close but not quite exactly the same? In that case, then their interference pattern is not going to be consistent through space. But we'll take a look at what's happening as far as their interference patterns through time instead. So here on the left, you have a wave where there are two waves that are both at a crest. This purple wave is oscillating at 50 hertz while the blue wave is oscillating at 60. Well, what happens is since they're at a different frequency, they pass through different phases at different times. So they start off together. They're both at crest at the beginning. But here, half a second later, notice that the 60 hertz wave is at a crest while the 50 hertz wave is at a trough. And so you're going to end up having destructive interference. I said that's half a second. I apologize. 0.05 seconds. Move a little bit later, 0.1 seconds later, they're back into constructive interference again. 0.15 seconds, you are in destructive interference again. So when we talk about the superposition of waves, we add these two together, and what we get is regions of constructive interference. You're going to have large amplitudes. Destructive interference, you're going to have little to no amplitude. Constructive interference, little to no interference. And as a result, you're going to get this wave pattern where the amplitudes are high, then low, then high, then low, then high, then low. Results in what we call a beat sound. Now, how often do these beat frequencies happen? Well, we can calculate the beat frequency by simply taking the difference between the two frequencies. So let me show you something here. On the right, I have a website, desmos.com/calculator. This is a really cool graphing calculator that you can use, and we'll go ahead and do this. We'll go ahead and do this with the same frequencies we just saw. So sine of 50x means it's a frequency of 50 hertz. 60x would give us a frequency of 60 hertz. Now I've got to zoom in. Let's see. Y-axis we don't need any more than -5 to 5. But the x-axis we're going to zoom in and go 2, 3. No, let's go to 2. There we go. This will work. So you see regions where you have constructive interference, moving to destructive, constructive, destructive, and we can zoom out and see the pattern continuing. You can see constructive, destructive, constructive, destructive, so on. Let's move back in. And now I'm going to add the two frequencies together. And you can see that they oscillate between large amplitudes to no amplitude, large amplitudes, and so on. And if I zoom out, then you can see this alternating pattern. If I were to play this for you, you would hear loud, quiet, loud, quiet, loud, quiet, loud, quiet, just kind of a wah, 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 wah type of effect. In fact, I have here an online tone generator that will actually play two sounds at once. Now, remember that we found that the beat frequency of this beat pattern is just the difference between two frequencies. So I have here 500 hertz and 503 hertz, both playing at the same time. They're not playing yet. They will in a second, which means you should hear, the difference would be 3 hertz. You should hear three beats per second. I'll play it for 10 seconds, and you should be able to hear 30 beats. So let me go ahead and play that. I'm going to pull up my timer so that I can time this. If I can get my phone to work. There we go. Okay, so I've got my timer up. I will time it for 10 seconds. See, and count how many pulses you get. 3, 2, 1. If you counted 30 pulses, that means 30 pulses in 10 seconds, 3 pulses in 1 second, so you got a beat frequency of 3. Okay, maybe that was a little hard for you. That's okay. Let's try something a little easier. Let's go 502, which means it should have a beat frequency of 2 hertz. If I play this for 10 seconds, then that means you should hear 20 beats. Here we go. 3, 2, 1. So I let that go for an extra second, so you probably heard 22 beats instead. But you should have heard either 20 or if you counted to when I clicked, you would have heard 20. But if you counted until I actually hit stop, you got 22 for 11 seconds, giving us 2 beats per second. Now, if you want to try this on your own, go ahead and go to this website. This is the website that we just used. Really fun website. You can play around with the binaural beats or beat frequencies. And Falcon Online, I have this link along with a few interesting pairs of frequencies that I want you to try. Put in those pairs. So just as a quick example here, let's say you have 2 flutes that are playing the exact same note at 440 hertz. However, but you hear 35 beats in 10 seconds. So if one of the flutes is exactly in tune at 440 hertz, how far off out of tune is the other player? Okay, so we have, I'm sorry, I thought I turned on my pen. Here we go. We have a beat frequency of 35 beats per 10 seconds, or 3.5 beats per second. Remember that your beat frequency is just the difference between, that should be F1. Beat frequency is just the difference between the two, which means the second person has to be off by 3.5 hertz, which means the second flute is either playing at 443.5 hertz or 440 minus 3.5, which would be, 436.5 hertz. So the second player is playing at one of those 2 frequencies. Either one will give you a beat frequency of 3.5 hertz.